Hi everyone, I'd like to explain here on how to actually compute this orthogonal projection using Mathematica. And here first I'm going to explain the algorithm. V is a vector space with the inner product given, and H is a finite dimensional subspace of this V that can be potentially infinite dimensional, and we have a definition of orthogonal projection. First thing we're going to do is first we choose a basis v1 through vn. This basis doesn't have to be an orthonormal basis or orthogonal basis, and that's one of the reasons why I'm doing this. And calculating that could be a little bit of cumbersome work to program it. In terms of amount of computation we go through by doing this method I'm about to introduce, or usual orthonormal method, I think it's comparable, but coding-wise, I think it's easier to do it this way. So H is any convenient basis. If H is a polynomials, this will be usual monomials, things like that. And usually we choose this V outside this H. In that case, V is going to make a slightly bigger space, as it's written here, but if V is happen to be inside H, this doesn't really make an independent set. And the answer to that case where V is inside H is easy, so we're not considering that part. So V is outside, so this is n plus 1 independent vectors. Now what we're going to do, we're going to find this vector E tilde, which is inside in here, and that is orthogonal to all the vectors in v1 through vn. So it is kind of cross product in this span of all this thing, cross product of all these v1 through vn. So one dimension left here. So a vector that is perpendicular to this hyperplane inside the span of these n plus 1 vectors, one way to say it. So as you can see there, n in linearly independent vectors, k going through 1 through n. But we have n plus 1 free variables, so the dimension of a solution set is one-dimensional. So it's a1 through an plus 1 will be parameterized by one parameter t, for example. So from the examples we're going to see, and by looking at the row reduction forms and things like that, and it's clear that you can set this an plus 1, any values is actually, if you find 1, all the scalar multiples will be in solution to this orthogonal condition. So we know it's a non-zero because of linear independence and things like that. So you can scale it to anyone. So if you particularly later on, if you set an plus 1 to negative 1, and this reveals a very convenient solution for us. So here, if you set that equal to negative 1 and compute the solution a1 through an for that choice, then it turns out this is really the projection. So amount of computation it goes through is to solve this k go through 1 through n and n linear equation. So this is going to be n by n plus 1 matrix, and reducing that is the amount of computation involved in here. So that's the idea, and I'm going to show you how to do this one in Mathematica. First, let me explain a little bit about the setting of our example. It's an interesting example that V being the vector space, infinite dimensional vector space with bases even uncountable, all a continuous function defined on this closed interval a to b, and H is this finite subspace, the polynomials of real coefficient up to degree n, and inner product is defined as usual integral from a to b of the product of two functions that we have. This integral in practice, using even computer software, takes a long time. Even numerical integration takes a long time. So I will compare these two methods with the slight change to this definition of inner product, which is just estimate of the inner product, which is this one. That whenever we integrate, we can actually substitute with this Riemann sum definition. Riemann sum goes like this, and well, by increasing n to 100 and 1000, and this calculation is a lot faster than even numerical calculation of the Mathematica. Mathematica try to check if their numerical computation is accurate enough and things like that. That seems like causes a little bit of a problem. So I might just replace it here, and then I'm going to go back to numerical integration of Mathematica or even exact calculation to compare the result a little bit. Alright, in this file I'm defining that Riemann sum, that's the number of division, 100 division, and here in this example the interval is 0 to 1. And I'm preparing the delta that is involved in Riemann sum. This is a precision level of the numerical calculation, so I call it a discrete integrate. So if I have a function p in x, it's an expression in x, then we're going to calculate this one. This is exactly the Riemann sum definition. And down here, I'm defining the inner product here. If I have two expressions in x, I'm going to do that discrete integrate of this function in here, going from a to b. And later we're going to compare that with the numerical integrate of the Mathematica command or exact integrate Mathematica command. So I'm hiding that part in here putting these stars, and that's a way to do it in Mathematica. Right, our target function v should not be a polynomial, so I'm using this sine function, and we're going to go up to degree 3, so that's our h. So I'm showing you the plan again. Here's the h is a subspace, a polynomial degree up to n, so I'm choosing 3. The reason I'm doing that is because the shape of a sine 2 pi x between 0 and 1 looks a lot like some other parts of the cubic curve. So hope we can discover a nice cubic solution that matches this condition globally from 0 to 1. Next thing we're going to do is we're going to generate the basis of h. Back to this slide, we're here at this stage. H is that polynomial degree up to 3. So we're generating basis. In this case, the base, there are 4 elements in the basis. Polynomial degree up to 3, there are 4 elements. So here, I'm creating a table of this element x to the 0, going all the way up to the x to the 3rd. So it is showing, not showing right above here, it's showing down there. It creates these things. Let me suppress the plot command. So we have these 3 things generated. 4 elements generated. And here next thing is that we're going to extend that basis with 1 more element, which is that sine 2 pi x. Right, b is that polynomial basis, and you can extend it by appending 1 element and redefining it. So bv is the extended basis. So if you run that, you can see we have 5 elements basis now. Alright, let me explain the next step. This is to target all the elements inside that span with the n plus 1 vectors. In our case, v is sine 2 pi x, and these are the polynomials degree up to 3. We're looking for all linear combination in here that is orthogonal to 1, x and x squared and x to the 3rd. So 4 vectors. So this one will serve as a kth row. This equation will be expanded as follows, like this, and you can treat it as if it's a dot product and vk distributes over like this. And these are unknown coefficients. We know what v1 is, that's 1, and v2 is x and x squared and x to the 3rd, and this vk is whatever the monomial in h. So by changing k being 1 through all the way to 4, b4 is x to the third, we're going to have 4 equations, and there are 5 variables. So I'm going to use this as k as index of a row, and a1 and a2, these are usual linear system of linear equations. So we can do this in Mathematica. Here it is. The table generates matrix or vectors and things like that. So it's convenient. You can prepare elements before you actually declare the entry in here. So I don't like all the brackets, so I'm just naming it differently. The BV is this extended basis, is a kth element in there, and this is a jth element, and k runs through, k is the row, number of rows, and k is also number of bases in the h here. So that's 1 through degree plus 1. A degree is not really the number of bases in here, is a plus 1 because of 1 in there. And j is including this v, so I have to put 1 more. And what we're entering is the inner product of this vk and vj. It's here. Let me show this again. So you can see that's the vk and vj. The order is not important, so if you swap the inner product, it's the same. So we're generating each of these in there. It's going to be a table. So let me actually compute that. Right, we're doing this numerical computation, so as you can see there are 4 rows and 5 columns in here. Alright, the solution to the null space to this matrix will be the coefficient a1 through a5 that we're looking for. Alright, so I reduced that matrix. I'm calling M reduction and showing in the traditional usual two-dimensional way. So as you can see, there's 1, 1, 1, and there is a free variable. The free variable we're going to choose here is -1. Right, I'm showing you this part again. So we have 1 free variable involved in here. We're going to choose free variables such that the last entry is a -1. And I claim that this one right here, and that's actually the projection. So we're over here, if you think about how this matrix works, then you can put that because of this is non-pivot, last one in here, that's a free variable. That last slot is actually that an plus 1 that I showed you. So if you put the -1 in there and solve for a1 through an, and this number as you see here is exactly the solution. So we want to isolate that one. You can do that by multiplying vector 0, 0, 0, 0, 1 in here, and that's going to isolate this one. The next part I'm doing that, so I'm creating zeros all the way up to degree n plus 1. So that's going to be matching the size of a base of h. And at the end I'm adding 1. So that strip is going to be a vector with a 0, 0, 0, 1 all the way to n. So if you multiply it here, it's going to isolate that. So I put in here, the coefficient part is the last column, so that matrix multiplied by this thing is that last 4 coefficients. So that's going to be the coefficient constant, coefficient of x squared, and x to the third, and things like that. So that's going to be the coefficient. How are we going to turn this one into polynomial? It's also simple. It's done like this. The coefficient is dotted to b. What was b here again? b is a 1 through x to the third. So if you hit it, that multiplies each of the element as if it is a dot product, and we have this thing. So that polynomial is supposed to be a good approximation of sine 2 pi x. And in this line, I'm sketching sine 2 pi x, and the projection we calculated between 0 and 1, and the projection that v's original function, which is in black, and projection is in red, I think. So let's see. Yeah, black is the original function, and degree 3 that we calculated like this. And if you compare this one with the Taylor polynomial, and Taylor polynomial is try to do approximation as best as I can on one point and more local. And this one is trying to minimize the area in between in here. So I scrolled up here and to do a little bit better. So if I increase the degree to a little bit higher, such as 7, and the computation time is quick, but it is doubting that our row reduction part is not absolutely good. So it says x to 7 is the best approximation. You can imagine x to 7 is not a good one. So I had to increase precision level, for example, to 50 and to 500 more division, and it did okay as far as I remember. So it didn't question the row reduction part. It gave you this polynomial. Now you can see it's nearly identical. We don't really see the black anymore, which is hidden under this projection. So it did fairly quickly, and we're going to compare that with actual integral, which is numerical integral done by Mathematica. So we're not doing my integral, it's a numerical integral set up in Mathematica, and see how long it takes with a degree 7. It did it quickly, but it is questioning that when they're deciding this numerical integrate is accurate or not, it doubted a little bit and it gave it this type of an answer, and you can compare that, it's still good. But when we change this function sine 2 pi x to something else like this, it's more complicated, like this one. Let me first sketch this function to show you the shape of this one. So I separated here so that we can see the graph first. So this is some of the things that I do in my pre-calculus to have fun with, to create a nice, interesting shape of the periodic function using the simple algebra in this one. So let's see how this is gonna do this one. So still I'm using this numerical integral of this function, and we have all that. We're still using degree 7, and it did it fairly quickly. So if you compare that, degree 7 is not very good, as you can see that it's very different. So you have to bump up this degree level a lot higher. As far as I remember, that was a 20, and I'm going to do that myself, and I'm going to show you just to show you the result. Right, I kept this division level and precision level, but I'm using discrete integrate version, and I'm going up to degree 20. I'm running it here, and it did fairly quickly. It took less than 2 seconds to get this one. It didn't question about the reduction process, and when I sketched it, it looks almost identical like that. And when you use a numerical integral of a Mathematica, so here I reset that inner product definition to n integrate, and here it's already done it, but it didn't do very well. Let me double check. I already did that in here, n integrate, and down here I'm running it, and it is doing the calculation, but the numerical calculation and the row reduction process, it was questioned, and it didn't give a very good answer. So disappointing answer from numerical integrate. And if you even change to integrate like this, as far as I remember, it took several minutes to do this exact calculation. I'm going to wait and actually show you this time how the reduction matrix looked like. So I'm going to insert in here, write that. I'm going to hit it, and it's going to take a long time, but I'll pause the video and let you know. Alright, it finally did it. It took about 2 minutes, and up to degree 2 using the exact integration. These coefficients we're looking for is actually rational numbers, because the function is nicely constructed using the rational multiples of pi x in there. So it is shown like that. It is not the form that we wanted. If you wanted to see that again, is mred. So you go to the next line. It's a long data. This is where the end of it. So we can do the traditional form of nRed. It's still going to bang, but you can kind of see it better in here. You can see the ones in there and to the right side, and that's an expression, the exact form of the number at a lot of powers of pi in there. So with that, it's going to generate a picture like that. I don't know what happened. It is disappointing anyway. So I guess numerical computation was better. Right, I came here and reset this integral back to this Riemann sum version, and I'd like to show how this polynomial evolves. To do that, we're going to do the following. I did that on purpose, in this way on purpose, so that everything is in this order. So all you have to do is to change this degree to something else, and we're going to go through the exact same procedure over and over and get this one in here. So even I'm going to include this time. So let me do this again. Include this time the plotting of at the end, and we're going to kind of turn that into a procedure so that we don't copy and paste or run and hit enter and like this, make this entire thing into a command. Once you know this procedure works fine, and you can turn that into a nice procedure as follows. So we're going to copy the entire thing in here from here to there. So I copied it here, but not the degree part. Degree part is going to vary. So in the next line, we're going to do this procedure. So I'm going to name the procedure. Here it is going to be orthogonal projection. Our main input is just this degree, and it goes like this. And then everything else, if you put degree in there, it's going to repeat this one. The next line, usually we do this module and like this, and you declare here's a local variable. Here we're using b as local variable, bv down there, local variable, m and mred. I'm going to list them all. Right, so I list all this local variable, then they changes to screen color, recognizing it's all done in here, and then you go to the end and close it like this and define. Now that's orthogonal projection. We know it's safe up to 20 with that precision level, so I'm going to experiment orthogonal projection of a degree up to 5, and then it's going to calculate quickly the degree up to 5 in here. If you want to go to degree up to 7, and that's going to be degree up to 7. So I'm going to see this all together into the picture and to kind of compare how they evolve and things like that. And the manipulate is the best one, so I'm going to show you how it works. Right here, I'm doing the thing that we just did. V is the original function, and I'm plotting this orthogonal projection to 5, A to B, the plot style. All right, then it's going to calculate and sketch. So when I did it, it didn't finish it. I realized that the common mistake that I make, and all the beginners make in Mathematica, is that if you use this x in here, and then inside the algorithm we use x for lots of indeterminate thing, and when we plot this one, these guys try to plot x equals something, and when we go through this procedure, it's going to generate turn that all the x's into actually a number. It's going to confuse that algorithm. It's supposed to be indeterminate. Whenever this type of thing happens, it's better to just generate all the pictures first and then call it in here. So I'm going to turn it into a table of all the answers up to, let's say, degree 20. That was saved there. All right. So I created all the formulas in here. So when we go through the algorithm, x remains an indeterminate. So there is this degree 3 up to degree 20 all prepared. So you don't have to compute it again. It took some time, but not too bad, less than 1 minute. 3 to 20 using our discrete integrate formula. All right, so v is the original function. All projection of the fifth element, whatever that degree is. I think it was degree 7. It looks just like that. But anyway, you can just call it like this. If you want a degree something different, 7th element or something like that, and let's go to 9, then it's going to be slightly better and things like that. So rather than just keep hitting an enter, you want to see this nice presentation and continually. So here is the way to do it. You just surround this one by manipulate like this, change that to degree, and connect, and down here degree varies from 3 to 20. That's not it. Degree is actually indexed in here, so I have to call it index. The number of elements here is 18, I think, so K goes from K1 through 18. Then it's gonna do the degree 3 and degree 20 and things like that. Alright, finally it did. So the first one is degree 3, and I could have added, indicating what the degree is here, but what you have to do is that K plus 2. So K is 1 and plus 2 is degree 3. So let's see how this one evolves as we go one at a time. I was wrong. This is supposed to be plus 1 in here so that it knows this increment is by integer, otherwise it's going to get confused. So increase of 1 through 18 increase by 1, so that's degree 3, and that's degree 4. As you can see, it evolves nicely. When it enters, odd degree doesn't change. Sometimes happen if it has the property of even and odd property something. I don't know what I'm talking about. Anyway, if you keep going like this, it evolves, but not. So this one's good, and one more doesn't change. And here is degree 11, I think, if you add 2. So degree 13 is almost good. So one more is almost identical in here. When you reach degree 15, it was almost identical. Alright, I hope that showed you some idea about how to implement our idea into general computer programming, and at the end I showed what you can do with Mathematica further, especially this animation. This manipulate is a really good command to present several different data all together into a nice form. Thanks.